Hi everyone, welcome back. I'm Celso Viana and this is my contribution to the third Geometric Analysis Festival. This is lecture number 3. So in this lecture and final video, I will present our main result on the classification of constant mean curvature hypersurfaces that are volume preserving stable in the real projective space RPN. Okay. So the plan for this video will be to explain this classification result and show how it gives as an application the solution for the isoperimetric problem in the real projective space of any dimensions. Okay, and in the remaining part of the video I will present the key ideas and also the key computations that we did in the proof of this result. Okay, so let's state our main result and recall here that sigma is a two-sided immersed constant mean curvature hypersurface in the real projective space, and the key assumption here is that is stable. Okay, and so according to our theorem, the possibilities are that sigma is a geodesic sphere, of course. And then the other possibility is the quotient of a Clifford hypersurface by the antipodal map. Okay, so this Clifford hypersurface is like a generalization of tubes about geodesic that we saw for the corresponding result in dimension 3. Okay, and also there is this other possibility of a twofold covering of RPN. Okay, so these are the only possibility for a stable curvature hypersurface in the projective space. Okay, so this result is motivated by another result of Ducarmo, Rittore, and Ross in the specific case of minimal hypersurfaces. And so hopefully I'll be able to explain the similarities and also the key differences in our approach. Okay, right. So if we look at this Clifford hypersurface here in the sphere as a family of hypersurfaces as r goes from 0 to pi over 2, you will check that they give you like an equidistant foliation. So each hypersurface is equidistant from one another, and they degenerate in some spherical subspace of the sphere, which corresponds to these dimensions here, n1 and n2. So using that observation, then there is a very neat description for the projection of this hypersurface in the real projective space. So they are just boundaries of tubular neighborhoods of projective subspaces RPK inside RPN plus 1. Okay, so for example, when k is 0, that corresponds to tubular neighborhood about a point, which are the familiar geodesic balls. Okay, so since we are talking about isoperimetric hypersurface in higher dimensions, these objects might have some singularities. Maybe I should say some words about the regularity in our theorem. Okay, so it turns out that there are some good cutoff functions that were constructed by Morgan Rittore and also by Jonathan Zhu, which allow us to localize the support of our test vector fields that we use in our variational argument, to localize that to the regular part of our isoperimetric hypersurface, right? And then eventually this cutoff function has a nice convergence according to these works. Okay, so one question you might have at this point is whether all tubular neighborhoods of RPK are isoperimetric for some volume. Okay, we know that for k equals 0 that's the case, right? And so in order to answer this question, so let me plot here the graph of the isoperimetric profile of RP7, And as you can see in this graph, the profile obeys some successivity property. For example, for very small volumes, then the solutions are of course tubular neighborhood of points, and then as the volume increases, then tubular neighborhood of geodesic become beta competitors, and then as the volume increases, then tubular neighborhood of RP2, and you keep following that order. And this successivity property was conjectured by Berger, and it should hold in any projective subspace. So you can include the real projective space or the complex projective space. So if you are interested in a given dimension, then you just plot the graph of these tubular neighborhoods, the area of these tubular neighborhoods, and then eventually you will see that this successivity property indeed holds, right? But the statement as something independent of the dimension seems to be a very tricky computation, and we didn't investigate that further in our work, okay? Right. So what can you say about the proof of this result? Okay. So in the proof of the result, we follow the main strategy of taking the pre-image of our hypersurface to the sphere because we want to explore the linear structure of the Euclidean space. So in that case, you have the position vector field of our hypersurface in the sphere, and you also have the unit normal vector field in the sphere, right? And these two vector fields satisfy these fundamental equations that we have here, okay? And the main strategy will be to explore these equations. So in particular, the vector fields we're going to use will be combinations of the position vector field and the unit normal vector field. Okay. So it turns out that the way the proof works, I need to divide the problem in two cases. First, the minimal case, and then the constant mean curvature case. Okay. And for the minimal case, this is a work of Ducarmo, Rittore, and Ross that we mentioned earlier. Okay. So essentially, they consider vector fields of this form. So they are again combination of x and n, and these products that appears here are just to make sure that the vector field is invariant by the antipodal map. That's very important. So what we want to do is to take coordinate functions for this vector field and use it in the stability inequality, right? And then you need to explain why we can do that, right? Okay, so being minimum helps you a lot in this analysis because if you look at the quadratic form quadratic form on these coordinate functions, you're gonna check after some computation that the expression does not depend on the parameter b. So that's an important fact. And also, if you look at this expression as a quadratic form on A, then the trace is also zero. It's very easy to check that it's zero because the norm of n and the norm of x is 1 because our hypersurface is on the sphere. Okay? And so the question is, can you choose B to make sure that the vector field phi is balanced? Namely, each coordinate is a test function for the stability inequality, right? And so that's indeed the case, and this was proved by Rittore, Ducarmo, and Ross. They show that this linear map is always an isomorphism, except when sigma is totally geodesic, when this linear map is zero. So it's important in this argument that the surface is stable. Since the proof explores some equations for this normal vector field. Right, and so once you know that this is a linear isomorphism, then if you integrate your vector field phi here, and then you solve the equation for B, then for any A, you can make this vector field balanced by choosing the correct B, okay? Right, so this can be done for any A, and since the vector field is balanced and the trace is 0, the only conclusion is that this quadratic form is identically 0. So that's how the argument works in the minimal case, right? And if you look at the expression for this quadratic form, it can only be 0 if the norm of the second fundamental form is precisely equal to n. And that's how they argue in their proof, okay? So once you get to this part, then they use a very famous result of Shern, Dukarm, and Kobayashi, which classified the minimal hypersurface with constant normal of the second fundamental form, the constant being this number n. And they showed that the only possibilities are the minimal Clifford hypersurface, so Clifford hypersurfaces that are minimal. So it's interesting that there are many Clifford hypersurfaces with many topologies, but they are all united in a very specific equation, which is this equation here. And the similar statement is not true for the Clifford hypersurface with a mean curvature different from 0. Okay, right. So that's how the argument goes in the minimal case, right? So if the mean curvature is not 0, then you still want to use the same vector field, or maybe do a variation of that. As you can see here, there is a minor difference, which is this minus sign that appears before the first term, which I will explain in a minute. Okay. So again, what happens if you look at the quadratic form for these vector fields, right? And so essentially, if you do that computation, you see that this parameter b does not disappear in the problem. And that makes the quadratic form algebraically very complicated, right? So that's the main difficulty in addressing the problem under their point of view, okay? And so if you look at this expression, there is also this vector field x that appears there. This vector field didn't play a role in the minimal case because it is tangent to our surface, right? And our vector field is normal, so when you plug those two quantities in the stability inequality, they will cancel out. Okay, so but the key observation that we notice for the Clifford hypersurfaces is that the second fundamental form obeys a quadratic equation such as this one, for some beta, some number beta, that of course will depend on the Clifford hypersurface you are considering, right? And so as you can see, this is precisely the expression that appears in this vector field x. So it was clear to us that this vector field x should play a role in our proof, right? And also it highlights the fact that this beta also should in a way detect the geometry of the Clifford hypersurface. So in other words, this parameter b should have a role in their computation. Okay. So our strategy after this observation was to study the quadratic form as a functional on this variable b. Okay. So we try to understand how the function behaves in terms of this variable. And so it turns out that to do that analysis, we need to consider the following functional. So it's a functional defined on a cylinder where the horizontal slice is just the product of the round sphere times the orthogonal group SON plus 2. And so you have these variables a, phi, and beta. So beta is any real number which corresponds to the height in this cylinder. So the picture is given here. So we consider the functional defined on this cylinder, but essentially it's just the quadratic form applied on the vector fields we considered earlier. Okay. Right. So in studying this functional, we tried to find the equations for critical points for this functional, And a key computation that we did show that when the mean curvature is not zero, of course, showed that if you have a critical point, then the vector field phi that we considered is balanced. So in other words, each coordinate function has average 0 over the surface. And so this is a very important observation because it finding critical points gives us good test functions to use in the stability inequality, right? So our next step was to prove the existence of critical points, right? And for that we used the finite mountain pass variational principle for finite dimensional manifolds, such as the cylinder we are considering here, okay? So, and then we proceed as usual, right? So we look at the inclusion of the horizontal slice in your manifold, and we looked at maps which are homotopic to that one. So essentially we minimize the functional in the image of this map, and then we try to maximize in the homotopy class associated to that map, right? So here we have an example here of a map which is homotopic to the horizontal slice, okay? So this is a max-min variational problem, right? And so that gives you this number M1, and of course you need to show that M1 is well defined, and eventually you want to show that is a critical value for our functional, right? And so essentially to apply this finite mountain pass principle, you need to show that the functional satisfies the so-called Palais-Mail condition. So namely, if you have a sequence of points in which the functional is bounded in that sequence and the gradients are in norm is going to 0, then you want to make sure that you can extract a subsequence that converges. So it turns out that this Palais-Mail condition is true in our case, and the way we prove that is again by looking at the vector field phi, right? Because this vector field is essentially what describes a critical point when you integrate, right? And so if this minimizing sequence is drifting off to infinity, is because the integral of the last term, if you normalize b, is trying to give you a kernel for this linear map in this lemma that appears here, right? Which is the lemma that was important in the minimal case. So it turns out that this lemma is also true in our case, and in fact we used this lemma to show that the Palais-Mail condition is indeed satisfied. So in the minimal case, this lemma was important to get balanced vector fields. So here we are using for a different purpose, but in the end it will imply that we have the Palais-Mail condition is satisfied, and so M1 will be a critical value for our function. And another important fact that we notice is that this number is always non-positive, this critical value. And the way you can see that is quite easy if you look at the picture again of our cylinder. So it turns out that if you fix the orthogonal map phi to be the identity, and you look at the quadratic form as in A, then you see that the first eigenvalue is always negative because the trace is 0, right? And as beta goes from minus infinity to infinity, then you get a curve in this cylinder, and that curve always intersects this green hypersurface there. And so that explains why the minimum of this functional is along any hypersurface homotopic to the standard horizontal slice is always, the infimum is always negative. And so in particular the number M1 is well defined, for example, right? On the other hand, since critical point gives you balanced vector field, that implies that this critical value actually is non-negative. So in particular, it must be 0, right? It must be 0. So if you have 0, then you now apply the variational characterization for test functions, and that will imply that the Jacobi vector field on this, the Jacobi equation on this vector field is a constant vector in the Euclidean space. Okay, so and now you just need to compute that quantity and try to deduce some geometric information on your surface, right? And this is the equation here. So this constant C, this constant vector C, just comes from the volume constraint that we have on the test functions. Okay, and if you play with this equation a little bit, you see quite easily that the norm of the second fundamental form must be constant. There is no other way for this equation to be true for all x, right? And once you get that the second fundamental form is constant, you just look at the functional again, and for the expression of the functional, and you see that you now have a bunch of critical points for that critical value 0, right? More precisely, for any A in the sphere, and if you fix the orthogonal map to be the identity and you fix this beta 0, then these are all critical points for the functional. And once you have that, you look at the vector fields associated to these critical points, and then you repeat the computation for the Jacobi operator on this surface as we did above, and eventually you see that the C that you have now must be 0, and once you get C 0, then the vector field X is also 0, because it's just the tangential part of that vector field, and so that vector field X will be 0 for all A, right? Which gives precisely that observation that we made for the Clifford hypersurface. And that's what you need for the classification, because once you have this quadratic equation, you get the conclusion that you only have two principal curvatures, and they are constant, right? Two principal curvatures and they are constant. So hypersurfaces with these properties are called isoperimetric hypersurface, and they have been classified long time ago. Okay, so for example, if they have only one principal curvature, they are umbilical, so they are round spheres. But if they have two distinct principal curvatures, which are constant, then that corresponds to a Clifford hypersurface, which is a product of spheres, and the dimension of these spheres will depend on those principal curvatures. Okay, so that's the end of the proof. Thank you very much for your attention, and see you next time.